Aging has long been a topic of debate among scientists, researchers, and medical professionals. One of the most fundamental questions is whether aging should be classified as a disease or simply a natural process of life. The implications of this classification impact research funding, medical priorities, and the way society approaches longevity and health. Many experts argue that framing aging as a disease is an incorrect premise. Instead, they suggest focusing on healthspan and lifespan as intertwined concepts that should not be separated. The United States faces unique challenges in terms of life expectancy. While it is one of the wealthiest nations, its life expectancy lags behind other developed countries. This discrepancy is largely due to a high mortality rate during middle age. Factors such as lifestyle choices, socioeconomic status, access to healthcare, and chronic diseases all contribute to this issue. Additionally, funding allocation in medical research often follows public interest and policy rather than objective necessity. The National Institutes of Health, NIH, plays a critical role in funding research, but their budget distribution is influenced by political and societal factors. The concept of healthspan, referring to the years of life spent in good health, is gaining attention. Many argue that the notion of choosing between healthspan and lifespan is flawed, as the two are intrinsically linked. A growing gap exists between healthspan and lifespan, particularly in the United States, and it is widening at a faster rate among women than men. Researchers studying the biology of aging emphasize the importance of addressing this gap through scientific advancements. One of the key challenges in aging research is the difficulty of translating laboratory findings into human applications. While studies on model organisms such as mice have demonstrated promising results, replicating these outcomes in human clinical trials remains complex. Researchers highlight the importance of shifting the focus toward interventions that can extend both lifespan and healthspan effectively. Physical, cognitive, emotional, and social well-being all play essential roles in aging. From a physical perspective, the ability to perform daily activities and engage in recreational pursuits is a significant determinant of quality of life. Many individuals express concern about losing their independence as they age, reinforcing the necessity of maintaining physical fitness. Funding for aging-related research, such as the Interventions Testing Program, ITP, has increased over the past 2 decades, yet there remains untapped potential in understanding and mitigating the biological mechanisms of aging. The NIH and other research institutions must balance their resources across various fields, including cardiology, oncology, and neurodegenerative diseases. However, aging research is often overlooked, despite its potential to impact multiple diseases simultaneously. If aging itself were targeted as a primary factor in disease development, numerous age-related illnesses could be mitigated. One of the debates in aging research revolves around the measurement of biological age. Chronological age remains the most reliable predictor of longevity, yet biological age tests attempt to provide a more personalized assessment. While these tests offer intriguing insights, some experts question their accuracy and relevance. They argue that evaluating various biomarkers, such as VO2 max, muscle mass, visceral fat, and metabolic health, provides a more comprehensive picture of an individual's aging process. The epigenetic clock is one method of estimating biological age, yet its validity is still under scrutiny. Some researchers hope that epigenetic algorithms will eventually replace many traditional biomarkers, but there is still much to be determined. The hallmarks of aging, a set of biological characteristics believed to drive the aging process, provide a framework for studying longevity. However, not all experts agree on their relevance or how they should be prioritized in research. A key question in aging research is whether epigenetic changes are merely correlated with aging or if they actively cause it. To determine causality, rigorous experiments are needed. Scientists debate whether reversing epigenetic changes could slow or halt aging, and if so, what the best approach would be. Addressing these questions is crucial for developing effective interventions. Cancer research and aging research often intersect, particularly regarding uncontrolled cell division and tumor growth. While cancer treatments focus on targeting malignant cells, aging research seeks to understand the broader biological mechanisms at play. The distinction between normal aging and pathological conditions like cancer must be carefully examined to develop targeted therapies. Senescent cells, often referred to as zombie cells, accumulate with age and contribute to inflammation and tissue dysfunction. Some researchers believe that eliminating these cells could improve health span and possibly lifespan. However, the evidence remains mixed, with some studies showing health benefits but inconclusive results regarding longevity extension. Pharmaceutical interventions like rapamycin and metformin have shown promise in extending lifespan in animal models, but their effectiveness in humans is still being studied. The mechanism of action behind these drugs involves regulating metabolic pathways, immune responses, and cellular repair mechanisms. However, determining the appropriate dosage, long-term effects, and potential risks remains a challenge. Another area of interest is caloric restriction and its effects on aging. Studies have demonstrated that reducing calorie intake can extend lifespan in animals, but whether the same benefits apply to humans is still uncertain. The interplay between metabolism, genetic factors, and lifestyle choices complicates the ability to draw definitive conclusions. The role of blood factors in aging is also being investigated. Some studies suggest that removing old plasma or introducing young plasma may have rejuvenating effects. However, the specific molecules responsible for these effects remain unclear. If identified, these factors could potentially be harnessed for therapeutic purposes. Aging research is continuously evolving, with new discoveries challenging existing theories and opening new possibilities. As the field advances, it is crucial to ensure that interventions are scientifically validated and applicable to human health. The integration of multiple research disciplines, from genetics to physiology to clinical medicine, will be necessary to develop effective anti-aging strategies. Ultimately, the goal is not just to extend lifespan but to enhance the quality of life in later years. By prioritizing health span alongside longevity, society can move toward a future where aging is not feared but embraced as a phase of continued vitality and fulfillment.